let's finish talking about, we're talking about saturation point, the boiling point of substances, and that they will stay at a constant temperature so long as the pressure is constant. Excuse me. So we're talking about how do we keep liquid nitrogen at 1 atmosphere pressure. Liquid nitrogen occurs at about minus 320 Fahrenheit. And we can use that then to preserve biological samples, reproductive tissues, stem cells, etc. So how do we do that? Well, if you have a vacuum, if you have some kind of a canister, a cylinder with a vacuum, that provides really good insulation. So again, if we look at the first law, right, let's say that liquid nitrogen is our system. Okay? So if we look at the first law, how do we do a first law analysis? Well, you draw your system. Right? So this is our system. The nitrogen inside here. If you look at the first law says in minus out equals change. Well, what comes into this liquid nitrogen in terms of energy? Well, if we've insulated this really well, there's no heat. And I don't see anything doing work to the system, right? There's no force being applied, so in minus out equals 0. There's no heat and there's no work. So that equals the change. Well, what are the types of energy that can change for our system? There's 3 of them. 3 types of energy that can change for our system. Well, kinetic energy, potential energy, and internal energy. So if it's stationary, there's no change in kinetic energy and no change in potential energy. And that just leaves the internal energy. So as long as I can really insulate this, and that requires a really good seal up here, which is not going to be perfect. You're going to have tiny amounts of heat transfer actually occur. You can't get a perfect vacuum, and it's not going to perfectly filter out all radiation. You're going to have a tiny amount of heat transfer, and you're going to have a tiny amount of mass move through up here. So you are going to have a little bit of air leak in. So this is not going to be exactly 0. But if you can get this close to 0, you get very close to 0, and if the internal energy of the system doesn't change, that means the phase is going to stay constant, meaning it's going to stay at liquid. So how do we hold biological samples in suspension? Well, you submerge them in liquid nitrogen, and you insulate the heck out of that liquid nitrogen to where it stays liquid nitrogen. At 1 atmosphere pressure, that's going to remain at minus 320 Fahrenheit. Okay? So we talked about water, right? We said this chart is for water, but we could draw the same chart for nitrogen. And so at 1 atmosphere, instead of boiling at 100 degrees C, nitrogen would boil at, minus, if it's so basically minus 200 C. Okay, you could draw a similar chart for any substance. Is kind of the point there. Okay, a couple other terms here: latent heat of vaporization or latent heat of condensation. Those are the same as you probably learned in chemistry class. We won't refer to those very often, but they are a thing, right? The amount of energy required to go through the liquid vapor, liquid gas phase change. There's also latent heat of fusion or latent heat of melting. That's the energy absorbed or required for a solid liquid phase change. So again, just terms that just to mention there. Those you've seen those in chemistry. Hopefully, those aren't going away. They are here too. We won't use them very often. All right. So back to this diagram earlier. By the way, this is, I think you can see this, but we'll just enlarge this. This is temperature on the on the y-axis, the vertical axis, specific volume, that's volume per unit mass, on the x-axis. Okay. Now, I've got myself a note here to draw. If I have a lower pressure, so we said at a lower pressure, right, so if I've got pressure less than 1 atmosphere, we said if I go to the Mile High City, if I go to Denver, where the atmospheric pressure is less than 1 atmosphere, the water is going to boil at a lower temperature. So this phase change occurs at a different temperature if the pressure is different. Okay, so at a lower pressure, lower temperature, lower boiling temperature. And if I go to an elevation or a location, or if I increase my atmospheric pressure, if I have a pressure greater than 1 atmosphere, what happens? Well, the boiling temperature, this flat line, the region where the saturation occurs, that's going to occur at a higher temperature. Right? And I could plot multiple lines. I can continue to plot more and more lines down this way, and I could plot more and more lines up this way. And again, each time you're going to have this flat-lined region where the phase change occurs up to a point. Right? So in this diagram here, we'll zoom in just a little bit so you can see that a little better. In this diagram here, so 0.1 megapascals, that's about 100 kilopascals, that's about 1 atmosphere. Or at a tenth of an atmosphere, or 10 atmospheres. So this is different lines of pressure, increasing going up this way, decreasing going down. And again, for water, there's this point, and for all substances, there's going to be this point up here called the critical point. Right? Notice you've got all these flat lines, and all of a sudden there's not a flat line. That point where there's not a flat line is what we call the critical point. But again, these phase changes we're saying are these flat lines, or what we call the phase changes. And again, there's a point where there's no flat line up here at the very top. We call that the critical point. The critical point is a pressure-temperature combination where there's no apparent phase change. All of a sudden, the substance is behaving like a liquid, and then all of a sudden, it starts behaving like a vapor. We don't see it boil off. We don't see that change occur. Now, I can't point to any substances and tell you, hey, this is a perfectly good example of a substance that's beyond the critical point where we would observe it at 1 atmosphere. I'm unaware of any substances that do that. If you find one, feel free to leave it in the comments for the rest of us down below. You kind of see this with the carbon dioxide. You've got solid dry ice, and all of a sudden, boom, it's a vapor. But that is a little different. That's actually below the saturation curve. But that's another substance we can mention briefly later. So I can't point to anything that goes from liquid and then all of a sudden, boom, it's a vapor. For water, just to kind of put this in perspective, that is 22.06 megapascals. That's about 220 atmospheres of pressure. Nothing we're going to observe here on Earth or even in crazy laboratory settings, most of us, unless you really get into this kind of stuff. Okay, so just understand it's a thing. There are properties that we can go look up, critical point properties for various substances. That's table A1 in your text. We'll talk about that multiple times. But again, it's just a point on this diagram where there's no flat line. Okay, so here's what we can do though. If I plot the temperature volume values, again, this is temperature on the y-axis, volume on the x-axis. If I plot temperature volume values where it's saturated liquid, that's at the beginning of these flat lines, and it's a saturated vapor, that's the end of these flat lines. If I plot all those points and I connect the two data sets, right, so let's go black ink on this. Right, so if I connect all the saturated liquid points and I connect all of the saturated vapor points, notice a shape emerges. We call this shape the dome region, the saturated dome region. Okay? So the saturated dome region is this region here where everything under the dome, we have what we call a saturated mix. Anything underneath the dome is somewhere in between the liquid phase and the vapor phase. Part of it's in the liquid phase, part of it's in the vapor phase, and the rest of it's going through a phase transition. We call this the dome region, the saturated dome, the saturated liquid vapor dome or region. So, normally when we draw a TV diagram, temperature versus specific volume diagram. It'll look something like this. And this is kind of a nice generic one. We don't have to label any values on this. All substances will behave in a similar fashion. If I've got T on the y-axis, specific volume on the x-axis, everything to the left of this dome region is going to be compressed liquid. Everything to the right of this dome region is going to be superheated vapor. The left-hand line is going to be the saturated liquid line. The right-hand line is the saturated vapor line. And then anything in between those two curves, right, within the dome region is going to be a saturated mixture. Okay, that is a TV diagram. That is a temperature volume diagram. You can draw this very quickly. Lines of constant pressure, notice, just kind of tend upwards, up, flat, up. And it doesn't matter what the pressure is, they all look about the same. That is a temperature volume diagram. We can also draw a pressure volume diagram, a PV diagram. Very similar to the temperature volume diagram. The difference is the direction of the lines of constant temperature. So here on the TV diagram, I would draw lines of constant pressure. On the PV diagram, I could draw lines of constant temperature. But notice, the way this diagram works is much the same. And again, just to make it big enough we can see it, pressure is on the y-axis, specific volume on the x-axis. Everything to the left of the dome is compressed liquid. The left-hand side of the dome is the saturated liquid line. The right-hand side of the dome is the saturated vapor line. Everything to the right of the dome is superheated vapor. Anything under the dome is a saturated mixture. And again, lines of constant temperature just trend downwards. Higher the line is up towards the critical points, and even beyond, the higher the temperature value is on the line. Okay, so how does all this help us? Well, and by the way, that's liquid vapors. Let's talk beyond that. If we talk beyond that, we can also include solids. Again, we're not going to deal too much with solids in this class. We're going to deal very little for what we're going to do with melting. We're going to focus mostly on the liquid-vapor transition, not going to focus much on the solid-liquid transition. But we can mention it. Mechanics work pretty similar. If we include solids on a PV diagram, it looks much like this. Now this is for most known substances, because most known substances will contract on freezing, on becoming a solid from the liquid phase. There are some substances, specifically water and a few others, some rare earth metals, molybdenum, germanium, I think. I don't know, you can Wikipedia that. There are some substances that will expand on freezing. The most common one, of course, is water, and it's quite important. So, water will expand on freezing, and so what this represents is this is kind of laid over. The dotted lines means that it goes over just a little bit and then back over. Again, nothing that we have to really worry too much about because we're not going to focus too much on the solid-liquid transition in this course. Okay, but let's keep moving here. Okay, now, and just to mention, notice there's this triple line down here between the liquid vapor and the solid vapor transition regions. There's this triple line. That's just kind of a neat thing to point out. We're not going to do too much with it, but it's neat to mention that there's a constant pressure and temperature where a pure substance can exist in equilibrium in all three phases. So what that means is that along this line, the substance can be melting at the same rate that it's freezing, and it can be vaporizing at the same rate that it is condensing, and all three phases can be in equilibrium. And we'll pick up there.